Hello everyone, welcome to the video lecture series of Theory of Automata and Formal Languages. We are actually studying unit number 1. I have marked as a unit wise, okay. So unit number 1 we are studying about finite automata topics. Okay, we have learned a lot of things about how to construct a DFA, how to construct NFA, conversion process, okay. So now we are into a part which will be like you are actually minimizing a particular DFA, a particular finite automata. Okay, so the topic today in this particular lecture is that minimization of finite automata. So you will be maximum times you'll be getting a DFA only to minimize. Definitely you have to minimize a DFA only. But you might get a question where you will be asked to get a minimal DFA from an NFA. So first you have to convert that NFA into DFA and then you can minimize that. Okay. So basically in this topic, we will be getting into a little bit of definition part and then we will look into two examples for this. Okay. Yeah, so firstly, if I ask you finite automata, actually why we need to minimize in order to get a, you can say, reduce number of states. Okay. The advantage of this particular minimization saves a lot of space, yes, while implementation of any kind of problems. So that means if you're having a very big automata, suppose a lot of states are there, and there is a possible or feasible way of minimizing that particular DFA, then it will definitely help you in saving a lot of space. Okay, so what we have to do in this particular topic is that what are the methods that you can follow up is we'll be following three methods, but basically in this lecture video series I will explain you with two methods only, but still I will try to give it to you the table filling method also, which is the last one. Okay, the first method is partition method, or also known as state equivalence method. The second one is Myhill-Nerode theorem. So this is also an important one if you are a student right now pursuing any university examinations. Okay, and the easiest one is the partition method. If you're attempting any kind of competitive exams like GATE, NET, okay, then in order to carry forward or in order to quickly do the minimization process, then partition method is an easiest one compared to Myhill-Nerode theorem. Okay, so first we will look into this partition method and with two examples, and then we will, in the next video, I will explain to you how to work with Myhill-Nerode theorem. Okay, so partition method actually says a few steps actually we have to follow, but here I will just simply let you know the steps. You can pause the video and you can note down all these points if you are making some kind of notes. Okay, but I will explain properly with these steps in an example. With an example, it will be clear to you all. Okay, so generally two states are equivalent. First one, if first state on seeing any input string goes to a final state, okay, and then the second state also goes to the final state, then final state might one more thing is that final state might not be same. Okay, so that is if P and Q are equivalent, okay, then these two are states. Okay, and then transition for P over any input alphabet must belongs to the final state, which implies that transition of a state Q over any input alphabet must belongs to a final state. So this condition I will explain to you properly with an example, okay, with the proper steps. And in rule number 2 or step number 2, they say that these equivalent steps you should know. Sometimes they might ask you, what do you mean by 0 equivalent? What do you mean by 1 equivalent? Okay, if the length of the string is equals to 0, then P and Q are called as 0 equivalent. P and Q are nothing but the states. Similarly, 1 then 1 equivalent, 2 then 2 equivalent. In general, we say is that length of the string is equals to n. That means both the states are n equivalent. So what's the concept behind this? We will take an example and I will let you know how to work on it. Okay, so this is an example that I brought for you. It's a very common example. If you see in any book, if you see in any lecture, you can find out this example. And this is the very easiest one to explain to you. Then we can move to other examples as well. Okay, so step number 1, always keep in mind while doing a partition method that try to delete all those states to which we cannot reach from the initial state. Now, can you find any state which we cannot reach from the initial state? From Q0, we can reach Q1 and Q2. There is no issue about that. From Q0, we can reach Q3 through Q1. Okay, so that is a possible case. So Q0 I can reach to Q4 through Q1, then Q3, and then Q4, correct? So there is no problem. So that means from initial state, I can reach all other states some or the other. That means there is no possibility of deleting any states. Okay. Sometimes you might get a particular DFA where we are having certain states. To those states we are not able to reach from the initial state. Then that particular state you need to delete. I will show you in the another example. Okay. So step number one is that it is satisfies, therefore no state to delete for the above state. Okay, now step number two, you have to draw a transition table for this. Okay, so this transition table I have already drawn for you, but you can cross verify it. Okay, now this is the transition table that I have drawn for you. For Q naught, if you see on A, for Q naught on seeing A, it is going to Q1 and it is going to Q2. For B, it is going to Q2. See? Okay. Similarly, I have drawn all the entire transitions for Q1, Q2, Q3, Q4. Since Q4 is the final state, so I have marked it as star. The transition table for a particular DFA or NFA, you already know about it, right? So if you are unaware of it, please go see my previous lectures, okay? Now, I will explain to you how to work with step number 4 and step number 5, where the equivalence process generally works. Okay, so one important thing that you have to keep in mind is that now step number 3, after going into step number 3, the step number 3 says that try to find out zero equivalent states. Okay, how to find out zero equivalent states? Separate non-final states from final states. This is what it says. Okay, now I have to separate non-final states from final states. So if we check over here in this transition table, which are the final states? Final states is only one, correct? So if I have to remove from final, if you have to separate from final states and non-final states, so there will be definitely two groups. One will be for Q4 and the other one will be for all the states. So that means we will be having, okay, therefore we will be having here Q0, Q1, Q2, Q3 will be one group and the other one group will be Q4. This comprises of the final state and this comprises of the non-final states. Clear? One important thing you have to keep in mind while working with this particular algorithm is one thing you have to check same set. Okay, and one more thing you have to check same state. Actually, this is not mentioned over here, and this is what I have asked you to memorize. Okay, or this will become an easiest option to understand. Okay, same set or group. Okay, on same state. Okay, what does this means? I will explain to you. Now, moving to one equivalent state, we have done this. Okay, now we can check that Q4 being a separate one. Okay, then Q0, Q1, Q2, Q3 are one group. So this is one group, and this is one group, and this is another group. Okay, now Q0. Okay, so first I will draw this particular state, the state transition table only. Okay, let me draw this, and I will explain to you how to find out the next group, next equivalent states. Okay. Now zero equivalent states is done. We have find out. Okay, from zero equivalent states, I will draw the other. This is from similar to what you have drawn. What you have drawn in your what you have got from your state transition table. Okay. Q3, then Q2, Q4, and then Q2. Okay. So now how to find out one equivalent states? I have told you these two things you have to keep in mind. Okay. Now first I have to check first group. First group is what? This one. It comprises of 4 elements, and the second group is Q4. So leave as it is. Okay, first we will check the first group. First group, I have to take the initial state. Which one is the initial state? Q0. Then with Q0 I have to take one more state. Okay, and I have to make a pair. Okay, Q0 and Q1 I have taken together, and on seeing A, where it is going, Q1, Q1. Which condition? Same state, so no problem. Correct? Now you come to understand what we are going to deal with. Then Q0 and Q1 on seeing A, where it is going Q1, Q1, that means same state, so no problem. Q0 and Q1 together, when we check for B, it went to Q2, Q3. Q2, Q3 are in zero equivalent, we are having in the same set or same group. So that means no issue. Clear? That means Q0 and Q1 we can come together. This is how you need to make a pair, okay, or how to group, okay. Now I have done with Q0 and Q1. Now taking the initial state, I will take with Q2 now, okay. Q0 and Q2 on sync A, it goes to Q1 and Q1. This is Q1, okay. Q1 and Q1, this means what? Same set, same state, therefore no problem. Then Q0 and Q2 on sync B. For both the input symbols, you have to check these two conditions, okay. Any of these conditions satisfies, then they can pair each other, clear? Q0 and Q2 on sync B, where it is going Q2 and Q2. This is also same state. So there is not at all issue that Q0 and Q2 can come together. But before that, there was already one element known as Q1, okay. So you have to also check with Q2 and Q1. Now Q2 and Q1 on sync A, where it is going Q1, Q1, same state, no issue. Q3, Q2 also in the same group or same set. So that means Q1 and Q2 can come together. That means Q0, Q1 and Q2 together, we can say that these three can come together. Clear? Now these three have no issue about that. Clear? Now we are left out with Q0 and Q3. Last element is left out. So I have to first check with Q0, then I will check with Q1, then I will check with Q2, because these three elements are together right now. Okay, now Q0 and Q3, when we check for A, input symbol A, this is same state, so no issue about that. For B, where it is going Q2 and Q4, oh, there is a problem right now. See, in zero equivalent state, Q2 and Q4 are in different set or different group. So that means Q3 cannot come with Q0. If Q3 cannot come with Q0, then Q3 cannot come with Q1 or Q2, because these three have already made pair. So that means these three will come together and Q3 will make a separate group. But before that, there is an alone group right now, Q4. So it will try once with Q4 as well. So now if you check with Q3 and Q4 together for input alphabet A, where it is going, same state, no issue. For B, it is going again with Q4 and Q2, but these two are in another set, another group. So that means these three, the Q3 and Q4 cannot make pair with each other. That means Q3 will be a separate group now, and Q4 has been a separate group earlier only. So these are the one equivalent states we find out. That means these three will be together. Okay, this will be a single pair and this will be a single pair. So finally, in one equivalent states, we got this one. See, now the condition comes over to two equivalent state. Whenever you are finding for, suppose you are finding for one equivalent states, you have to check these two conditions for the previous one only. Suppose I am finding out for two equivalent states, I have to check these two conditions for one equivalent only. Zero equivalent is done. That means predecessor, the exact predecessor you have to find out. Clear? Okay, now these are the one equivalent states I have find out. Now how many groups are there now? 3 groups are now present, okay? So these two are alone. So first I will check with this one, okay? Now moving to two equivalent states, okay, there is a problem. This is empty. So let me write down the things. So in two equivalent Q0, Q1 and Q2, they are coming together. The transitions will remain as it is, okay? Q1, Q1, then Q2, Q3, Q2, okay? Then again Q3 is left out and then Q4 is left out. Q3 will be Q1, Q1 and this will be Q4, Q2, okay? You know that this is already a separate state, okay? And this is one separate state, separate group, okay? So now first we will find out to check these three, okay? How to find out? Same process. First I will check for Q0 and Q1 on sync A, where it is going, same state, so no issue. Q0 and Q1 on sync B, where it is going Q2, Q3. Now I have to check this condition for one equivalent. Okay, oh my goodness, this Q0 is in another group, Q3 is in another group. So my question to you is that Q0 and Q1 can come together? No, they cannot come together, because for this input alphabet, it is present in two different states. So definitely it will not come together. So now Q0 will make another group and Q1 will make another group. But before making a group, Q1 will find out to check with Q3 and Q4 first. So let me check now. Q1 will check with Q3 first. A, for input alphabet A, same state, so no issue. In input alphabet B, Q3 and Q4. Q3 and Q4 are other groups. So no issue about, so that means a problem. So Q1 cannot make a pair with Q3. So Q1 will try now with option with Q4 as well. So same state, Q for input alphabet, there is no issue. For B, Q3 and Q2 earlier it was in other group. So Q1 cannot make a pair with either Q3 or Q4 or with Q0 or Q2. Okay, so that means Q3 will make a Q1 will make a separate group. Okay, now I will now find out Q0 and Q2 because I'm concentrating right now with these group, right? I am not concentrating on these two because these are already a single one. Okay, now I will try to check with Q0 and Q2. So Q0 and Q2 on seeing A where it is going, same state, no problem. Then for B, Q2, Q2, this is also same state. So that means my problem is solved. So Q0 and Q2 can come together. Clear? So Q1 was already absent, a single one. Then Q3 was already a single group and Q4 was already a single group. So that means in two equivalent states, I found out to be like this. Clear? So my two equivalent states are done. Now in this way, you are thinking that till how many times you have to do it until you find out any two equivalent states similar. Suppose in three equivalent states, I find out to be the same groups. Then I have to stop there and I have to find out, I have to declare that these are the final states. Clear? So let me get back to three equivalent states now. Okay, so this is your three equivalent states, step number 6. Okay, I have already drawn this particular table, which is based on my two equivalent states. In two equivalent states, I find out to be Q0 and Q2 will be in the same group. Q1 is a separate group, Q3 is a separate group, and Q4 is a separate group, right? So if we check again, that how to find out. Now these are the single groups, so no need to check. I have to check only this group because this is a combination of two states. So let me check again. Q0 and Q2 on seeing A where it is going, same state, and on B it is going with the same state. So can these two pair each other? Yes, definitely these two can pair each other. So now the three equivalent states Q0 and Q2 will came together. Then Q1 was already a single state, no need to check. Q3 was a single state and Q4 was a single state. So can you just let me know that what you got in two equivalent state and three equivalent state, the same groups you got it. So do you wish to again continue? No, you can stop over here and you can finally declare that these are the final states that you have got. So that means Q0, Q2 earlier it was single state, now it will make a pair. So Q0 and Q2 will make a pair. Clear? So this is your initial one because Q0 was initial one. Clear? Now what was the final states? Final state was Q4, correct? So Q4 will remain as it is. Then Q0, Q2, then next will be Q1. Next will be your Q3 and next will be your Q4. So Q4 being a final state, so I have drawn this. These are the states that I have drawn. Now we can check with the table that on seeing Q0 and on seeing Q2, both for Q0 and Q2, on seeing A where it is going to Q1, correct? So directly I can draw A. From this transition table also you can find out, okay? On seeing B where it is going A to Q2, correct? So Q2 is this one only, so I will take a self loop. Clear? Okay, now I'm left out with Q0, Q2 is done. Now Q1 on seeing A where it is going to itself only. So then Q1 on seeing B where it is going, Q3. Clear? Then Q3 on seeing A where it is going, Q3 on seeing A where it is going, Q1. Q1 is this one, so clear? Then Q3 on seeing B where it is going, Q4. Okay, then Q4 on seeing A where it is going, Q4 on seeing A where it is going to Q1. So that means this will be your A. Q4 on seeing B where it is going, Q2. Q2 is here, so I can draw like this. Okay, so this is your final diagram for your minimized DFA. So earlier the diagram was like this. Clear? Now the diagram has been reduced to how many states was there in the previous one? 1, 2, 3, 4, and 5. Correct? And now we are left out. Now we are left out with 4 states: 1, 2, 3, and 4. So this is your minimized DFA. Clear? So now moving to the next example, you can please check it out in the next video. That will be an extended part where we will be discussing 2 more examples for minimization of DFA. Okay, we will start off with example number 2 in the next video, and we will also check one more example number 3. Okay, thank you for watching. We will meet in the next one.